Hello, everyone. Welcome to the third official episode of the ProLabs Podcast. On this podcast, we talk about everything there is to fiber optics, trending news stories, product reviews, as well as expert discussions about the best networking solutions out there. My name is Jon Eikel, and I'm the Chief Strategy Officer at ProLabs. And joining me today is our co-host, Ray Hagen.
Hey, thanks, John. As you mentioned, my name is Ray Hagen. I'm the Global Product Line Manager here at ProLabs. The topic of this episode is to talk about all the exciting innovations in the access layer network technologies. So, John, when we say access network technologies, I take it, being, old telecom guy, that this is the fiber getting closer and closer to the customer. So I know we've talked a lot over the last year or so about DAA, and that distributed access architectures. And really, what does that mean? That's the bigger thing a lot of customers say. So could you explain to us a little bit about what you consider DAA to mean to the customer?
Sure. So I think the DAA architecture was probably birthed in the idea of HFC distribution. However, we're starting to see DAA architectures that apply to PON as well. But it's the idea of pushing more of the intelligence, whether it's remote PHY or remote MAC-PHY, out of a centralized location, whether it be a hub site or a central office or wire center, out into some type of field cabinet or field node that's either side street mounted or strand mounted. So deaggregating and decentralizing some more of the processing of the users in traffic that allows these telecommunications providers to scale beyond what the walls of their existing buildings might allow them to, if everything remained completely centralized.
Got it. So this is almost sounds like a real estate issue then, right? Where
I think at the end of the day, it helps expand the ability of scale and bandwidth, whether the access medium is coaxial cable or fiber optic or even DSL. Beyond, as you mentioned, not just the real estate, but power and cooling and the limitations that exist in some of those buildings that were built, in many cases 20, 30, 40, 50 years ago.
Yeah, that's a great point. Great point. So where are we at right now in the DAA continuum, if you will? If we're starting out with HFC, hybrid fiber coax, where are we at on the continuum?
So I think the adoption of DAA, specifically with North American cable providers, is very much in its early infancies. So you've got, a couple of big providers that really dominate the U.S. market, and then a handful of true tier 2 cable providers, and then quite a few still small tier 3 providers. What we're seeing for distributed access architecture, at least with one of the big providers, is the marrying of that plus a virtualized CMTS solution. So not just pushing the Ethernet or IP network further into the network at the transition to coax, but also the removal of kind of big iron CMTS in favor of virtualized server-based or cloud-based architecture. So we're certainly seeing a large-scale field trial go on with one of the two major U.S. Cable operators. The second major U.S. cable operator has not made any public announcements or field trials, but we know that they also must be well down the line with DAA engineering and architecture solutions.
All right, great. So if I'm hearing you correctly, so it sounds to me that we're pushing digital now right out into the field, and so this digital conversion or whatever you want to call it is really located, in the head end or then it's working its way out to the edge. So what sorts of differences in technology between the current analog technology and the digital technology? What's the impact there to the network and to the customer?
Yeah, so if we think about traditional hybrid fiber coax networks that cable operators might have built, 2 or 3 years ago, you would have a CMTS, the cable modem terminating system, that would be located in centrally in a hub. The CMTS would generally output RF energy, so a F connector or some type of physical coaxial connector. That would go through a series of combining networks to combine other downstream services like video or out-of-band management for set-top boxes and pilot signals. those would be then injected via RF into an analog laser. And that analog laser would operate either at 1310 nanometer or 1515 nanometer and broadcast a downstream analog signal to a node, where the node would then receive it in the field, convert that analog signal back to RF, and then the signal would travel RF through hardline coaxial cable and amplifiers, through a tap, through a drop, and into a customer's home. So the hybrid fiber coaxial network in the downstream was mostly analog, and in the upstream followed a similar path, although the laser may or may not have been digital, depending on the node platform. But by and large, no IP to the field. So you had kind of proprietary analog and digital mediums that were transmitting these signals over the fiber into the field node and then converting back to RF. And with DAA, the idea is that we push the IP network over standard fiber optic, either 10, 25, or 100 gig transceivers, all the way to some field node. And at the field node, the intelligence begins to exist that converts those RF signals directly to IP instead of through a physical analog layer medium in both directions. So yes, at the end of the day, we're pushing IP, service provider IP core closer to the edge.
Got it. So then at the same time, the service providers are reusing that existing fiber plant they perhaps had for the HFC network, and it limits then the amount of fiber they have to build then all the way from the wire center towards the customer. Maybe they can branch off in spurs or what have you with a digital, IP pushing it further might make it a little bit easier for them to do so.
It definitely drives scale into that existing fiber network. So you can take existing strands of fiber and run many 100 gig signals down that fiber, terabits of or terabits of information rather, down a single pair of fibers. And then, the cable operators have done a terrific job of pushing fiber further and further into the network. So as node sizes have continued to decrease and bandwidth continues to increase, and cable operators have moved from series of cascades, if you will, of up to 30 amplifiers down to generally node plus 1 amplifier or node plus 3 amplifiers. The fiber has inherently gotten closer to the customer anyway. And it sets them up for very good continued realization on their HFC investment, but also sets them up for kind of the future, which we'll talk about, I think, later in this podcast, for going directly fiber to the end user, or PON. Right. So it enables them to take a very natural pathway to fiber all the way to the premise without abandoning a terrific investment that they've made in HFC.
Right. I think that that's that coax element to the home can still push a lot of data, a lot of services today that maybe a twisted pair infrastructure could not. So yeah, they're definitely that side of the house is.
I think, specific to DA architectures and kind of the transceiver world that we operate in, the move from analog lasers to transceiver and IP based has required a huge concern or consideration of retooling and retraining of what was the traditional cable plant technician or cable plant engineer. And so as we think about transitioning from analog lasers, you have technicians and engineers that are very familiar with light and fiber and splicing, but they may not be as familiar with IP-based networks and transceivers and how those devices work. And we talk about wanting to take a single pair of fibers and operate dozens, if not many dozens of nodes at the end of it, and needing DWDM access technologies and transceivers that would need to be tuned to specific frequencies during a repair or a regroom of a DWDM line. So that kind of leads us to, ProLabs' Clarity Autotune solution, which really enables and powers that DA architecture to be virtually plug and play. And Ray, I know you were instrumental in our product line development of that product. You want to talk for a minute kind of about how it works and the benefits?
Absolutely. We could probably spend an entire podcast talking about the different tunable technologies, and maybe we will, huh? Precursor there. But, one thing that the Autotune or Clarity Autotune, where it brings to network elements is, tunable optics, tunable DWDM optics, pluggable optics have been around for a little while. Most of the time it was, the actual tuning of the optics was done through a CLI on a switch. And a technician would have to, be trained in using that CLI and then tune it to the right bandwidth, sometimes frequency, depending upon how finicky the system is, that sort of thing. It sounds great. Probably not all that. Probably a well-trained technician can pull it off pretty easily.
And not all the platforms support tuning natively,
well,
right?
that's exactly it. Not all do. And a node, right, DAA node certainly does not support that kind of tuning. So what the Clarity Autotune solution does is it actually brings the tuning technology onto the transceiver itself. It can then bring that to other hosts that don't support tuning by simply plugging it. The two transceivers send out pulses until they pair up with each other, establish link, and essentially they're done. So almost plug and play type of provisioning of that and tuning of that DWDM connection.
So Ray, the Clarity Autotune allows you to take a kind of a non-DWDM aware device, put DWDM optics in it, and not just have them operate, but also operate somewhat automatically, where they figure out which mux port you've plugged into. As long as they're plugged into the same mux port on both ends, they find their frequency, tune, and just operate.
That's exactly it. It's not all that complicated. They just simply send out pulses of a light for the right bandwidth or until they reach each other, and they say, oh, you're channel 21. Oh, you're channel 21. We're paired, we're good to go. So that's essentially how it works.
It's interesting that having been in the business so many years, to see transceiver technology evolve where that much intelligence begins to exist on the transceiver. And it just continues with next generation coherent optics and more intelligence shrinks and gets put on pluggables.
Yeah, I think more is to come in that area too. When it comes to this sort of intelligence, we're going to be able to see from optics in terms of remote monitoring and things of that nature. There's more to come for transceivers.
Well, Ray, we've talked a little bit about DAA and kind of the move from centralized access solutions and big iron to more distributed access solutions for HFC specifically, and the benefits of scale and the ability of the operators to maximize that HFC footprint while kind of preparing themselves for what might be next with PON access architecture. And I think that leads the conversation really well into what's going on really with the more traditional telcos who had that legacy, somewhat crippling twisted pair infrastructure, who finally, I think, realized we've reached the end of useful capability of twisted pair. So we came out with 30 different flavors of DSL and increasingly better throughput performance. But at the end of the day, I think the telcos have figured out that their evolution is fiber to the premise.
Well, that's exactly it. Fiber to the home and PON, it's actually not a new thing. I remember working with telcos back in 2005, 2004 on the really first scale fiber to the home deployments here in the US. And at the time, there was some fiber to the home done in Asia, especially fiber to the unit, a little more MDU type things. But here in the US, and that's when it really started to take scale with with some major service providers, offering that scale for the whole industry to use. And GPon was the first, was actually the second generation technology for PON. The first generation of technology for PON was called BPon, or broadband PON. And when the early adopters of this BPon, when they decided that we need to upgrade to GPon, and essentially GPon meant gigabit PON, and it meant a gigabit on the upstream, they really had to do a forklift upgrade from the BPon system, take that old system out, put GPon in order to upgrade that line to GPon. They both transmit over 1310 upstream and 1490 downstream.
So no overlay and intercompatibility.
You may have an overlay of 1550 RF video on your BPon because it didn't really support it. And on your GPon, if you didn't have IP video, you probably had to you probably just did the 1550 anyway. I think most, just from my past experience, a lot of the providers who had a a plant kept the 1550 RF overlay anyway because they thought it provided a higher quality video image.
Okay.
I think things have changed today with IP video being much better than it was, I guess that was 15 years ago now. Holy cow. Anyway.
Don't date us, Ray. Don't date us.
So, one of the big things of PON technology, it's, one thing they've, service providers have really done is they tried to maximize the OLT. So when they talk about OLT, that's the single port on the card that would then go to a passive fiber optic splitter that would then distribute to each individual home. So it'd be a single fiber to every home. So we talked a lot about DAA, and there are still electrical and active components in the network. Whereas PON, passive optical network, there are no active components from OLT to ONT. So from the main end to the stopping end, there are no active components. And that really helped those service providers reduce their maintenance costs on that network. That was a big driver.
Plant maintenance would have to go way down with nothing but, fiber splices don't have electronics, and therefore they aren't subject to the same break fix, I think, that
exactly
you see with other access mediums.
Exactly.
Ray, we talk about PON, so like conceptually it's a passive optical network with splitters and fiber infrastructure, but you started with BPON, and then you talked about GPON and this natural evolution. And if you spend any time in the SP arena, you're going to hear about a dozen other types of PON. And it kind of reminds me of DSL and ADSL and ADSL2 and XDSL and VDSL and VDSL2 and HDSL and 30 other DSL flavors. I feel like we have a similar situation going on with PON, perhaps not quite as complex and in many cases more interoperable. But do you want to talk about kind of the differences between GPON and EPon, and then this kind of industry move that we see from GPon to XGS-PON, or even a combo architecture? Would you kind of want to elaborate on what that looks like and why?
Absolutely. So we need our secret decoder ring, right? That we all need to have here just to kind of, okay, this is without, anyway. The EPon and GPon were the two deployed technologies probably since 2006, 2007, up until very recently. The choices were either GPon or EPon. And EPon was primarily deployed in, say, maybe European markets, perhaps in Asia, or with the MSO market, whereas GPon was very much deployed by telcos in general.
And Ray, what is the core difference between the two?
Yeah, so EPon is one gig symmetrical upstream and downstream, that shared bandwidth amongst the people on that PON or on that splitter. And the other fundamental difference is Ethernet based. So EPon stands for Ethernet. GPon had a bit of an Ethernet underpinning, or not Ethernet, I'm sorry, ATM underpinning to it. So more of a timing piece of it, whereas Ethernet was Ethernet packets,
So a collision based versus time based.
Exactly. So, the GPon was perceived as having a little better performance, perceived as such. EPon served the bill for the customers who had it.
Did we see kind of the telcos? I think you kind of mentioned it, but GPon had that ATM underpinning and discrete voice channels based on that versus EPon, which was kind of a more ubiquitous IP and Ethernet access medium. So do you think the telcos kind of favored GPon because it kept that kind of that sacred voice traffic separate for quite a long while?
I think that was the, definitely makes sense why that was the underlying, the ATM was familiar. They knew that was a voice quality technology, and, from companies that voice service, provide voice service for 100 years, very much a, what they are familiar with, and wanted to make sure that they could still provide high quality voice services, high reliability.
And I think, as VoIP has evolved, we're seeing more and more, even core legacy telcos moving to, voice over IP services. I think the protocols have improved, and certainly the scale of IP networks has improved, the bandwidth.
Yeah. I think as long as the regulations are in place for lifeline voice, you're not going to see that change.
It's not going to disappear completely.
Yeah. Whereas the MSOs don't have that regulation. When they provide voice service, it's not lifeline voice.
Right. The we talked kind of a little bit then about the difference between GPon and EPon.
Yeah.
When we hear like GPon and XGS-PON and combo PON, can you talk about kind of what's going on in the industry with that?
Absolutely.
Why the move to XGS-PON, and what does combo mean?
Yeah, absolutely. So, one thing that the next generation of PON services are here, and it's called on the GPon side, it's 10 gig PON, or X for 10, 10 gig PON, 10 gig GPon, and that 10 gig GPon XGS-PON is 10 gig symmetrical, upstream and downstream 10 gigs.
So unlike GPon that was somewhat asymmetrical with what,
Right.
2.5 and 1.25 ish,
Right.
we now see a true 10 gig symmetrical service.
Yes.
Is that driven by business services, or what's driving the need for symmetry?
There is an asymmetrical standard that was introduced at the same time called XGPON, which was 10 gig down and 5 gig up. But at the end of the day, I think it's just a matter of, why are we messing around with asymmetrical any longer? Upstream bandwidth is a very real thing. And if the technology is there, let's use it. I think.
Well, and we talked about that upstream with the telework and COVID-19
absolutely
on a previous podcast. So we're certainly seeing the need for consumers to have more of that upstream bandwidth in their homes.
Absolutely. And one thing, absolutely, with XGS-PON, probably the big thing for service providers is the ability to coexist with GPon. And what does that mean? It means that the two technologies can exist on the same network. They're operating at different optical wavelengths. So XGPON is operating over 1577 downstream and 1270 upstream, whereas GPon is 1310, 1490. So on the same optical network, off the same splitter, they can provision different customers for different services based upon their subscription level. So it does provide a lot of for business services, for wireless backhaul, for high value home residential services. It offers them a lot more flexibility to be able to do that.
Truly maximizing that fiber investment.
Absolutely, and there's a couple different ways they can get these services to coexist. And the first way is using a regular, a coupler, a WDM, to passively combine GPon and XGS-PON under the same fiber infrastructure. And the second way is actually what you mentioned. It's called combo PON. Combo PON's a relatively new thing, and there's a few access platforms that are offering this functionality. And it has both GPon and XGS-PON technology, or lasers, if you will, and receivers in the same package. Meaning from the same transceiver, you can, using the switch, you'll tell that transceiver, to use the XGS-PON or GPon from the same transceiver. So it saves
simultaneously out of the same transceiver? Wow.
Transceiver.
So the really good kind of evolutionary model. So if you had a provider that was GPon based today, they could upgrade the OLT optic or the OLT port and overlay XGS-PON right on top of that GPon without touching the existing customer premise.
Yeah, absolutely. Or even just so it's easy as dispatching out a technician to simply swap out an SFP at the home. So
that's
a really low touch upgrade model.
Ray, are we seeing big adoption on XGS-PON? There's always a cost and benefit curve to the adoption of new technologies. So new technologies come out, they cost more money. They may or may not fit a current business model. Are we starting to see that adoption of XGS-PON, or is it still too new to be highly adopted in the SP world?
I think over the last 7-8 months, for obvious reasons, XGS-PON is gotten a lot of interest from all of our customers in general. XGS-PON is being deployed in limited, or I guess you should say in trials with the biggest telco carriers in the world right now. And they are looking to use it as part, not all, but part of their strategy as they look to broaden their fiber to the home coverage to their customers. I think that's the key thing. Part, but not all. Do
you see a point? So GPon will continue to live on for quite a while as a lower cost solution. Do you see a point where GPon kind of fades away into the sunset and XGS-PON just becomes the de facto standard?
Yeah, I think there's a couple factors why that might happen, and one is the increased split ratios that XGS-PON has. XGS-PON can split up to 128 splits, whereas GPon can, so it's 120 homes per OLT. So it brings the economics to that OLT down. It brings it into the ballpark, if not on par with GPon.
Is that because of higher transmit and more sensitive receivers, or what gives it the ability to do that much greater split ratio?
Yeah, it's got a little bit higher link budget to it. There's a few other options there. You've got, they've got, in the regular transceiver world, we're used to SX, SR, LR, LX. They got their own nomenclature here for GPon that can sometimes get a little hairy for people, like B+, C+, D, N1, N2, E1. So there's a few different things out there, but overall, I think the technology itself is designed to be able to achieve and strive for that higher port density. So I think that's the big thing going for it. Along with a little better, additional link budget.
Within ProLabs, you've really helped pioneer the deployment and productization of our PON portfolio. So just everything from legacy GPon and EPon up through these 10 gig and combo optics. Is ProLabs providing kind of the full gamut of transceiver solutions? Are there yet more new transceivers coming, or is the portfolio somewhat filled out and we're in an operating model?
Yeah, we've got, for what's being deployed today, we've got perhaps the widest portfolio or everything we need or everything that our customers need today. I think right now we're adding we're looking at adding some new things on the GPon side. We're going to add what they call a D optic. We hope to add soon, which will be, the old B+ optic, 20 kilometers, C+ optic, if you're thinking 1x64 optics on GPon. And now with D, you're really looking at pushing that for maybe a 20 to 40 kilometer range, depending upon your split ratios, to beyond 40 kilometers potentially with D technology. So that's something we've got in our sights down the road. We're also looking at making sure that we're offering a complete iTemp solution across the board with all of our GPon optics, because we're seeing, in places like in the MSO world where PON optics are being placed into these nodes as part of their DAA strategy.
Sure. Well,
so,
and
we
any
need to
kind
make
of
sure those are iTemp.
Yeah, any kind of distributed architecture is going to require iTemp because it's no longer in a climate controlled data center or telecom facility. So Ray, we talked a lot about coexistence and the kind of the natural progression from GPon to XGS-PON. Is there anything else exciting coming in the PON world?
The PON world, which things are shaping out right now, the next kind of big thing down the road is going to be 25 gig and 50 gig PON.
And so you think that we won't go straight to 100 gig. There will be a natural progression to, I'm going to say lower speed jokingly. When I started my career, 1.5 megabit T1s were really high speed. So, and we thought we'd never exceed the unbelievable bandwidth of 100 megabit fast Ethernet. So I jokingly said, but do you think these lower, quote unquote, lower speed PONs will come as opposed to a natural jump to say 40 or 100 gig?
Well, where I think these are going to fit into the overall scheme is going to be with 5G networks. Okay. Where they're going to be using this 25 gig and 50 gig to help feed from a 50 gig 5G interface out to various antennas in the field, or to or to feed other distributed units or central units out in the field. So I think that's where we're going to see a lot of those initially fit into the fold. But that's probably going to be some time in next year, 2022 perhaps, before those come on the steam. So that's going to be a little while. So we'll add that to one of those future podcast topics, like you mentioned. Future, way off in the future, yes. All right, guys. Well, I think that's going to do it for this episode. I want to thank everybody for listening in to us in this episode of the ProLabs Podcast. Please follow us on whatever podcast platform you're listening to us on, and also subscribe to the ProLabs YouTube channel if you want to see the video version of this podcast. For any questions about ProLabs or any of our products and solutions, please visit our website, www.prolabs.com. Thanks again, and we'll see you in the next episode.